In this video, I will be demonstrating the oil separation tutorial in TransAT. We will be looking at a separation of oil, gas, and water. Through this tutorial, we will use the phase average mixture model with the algebraic slip model, and we'll use advanced initial conditions. So you will learn how to load and compile initial conditions from a file. Our problem is as follows. We have a mixture entering a separator, and the mixture consists of gas, oil, and water. At the bottom, we have two pumps, one removing oil and the other removing water. Through the top, we have gas exiting through a pressure boundary condition. Our problem is set up as 2D and unsteady. Here, I've shown the results so you can get an idea of what we expect to see. We have our mixture entering and each phase exiting. To begin our setup, we'll need to define our geometry. This is a little bit too difficult to do in TransAT, so we'll be loading a GTS file. To do so, under the Mesh tab and Objects, load an object. Navigate to the tutorials installed with TransAT. And under the oil separation tutorial, load the reservoir GTS file. We'll confirm that this will reset the mesh, and we'll import the object with units of meters, and we'll confirm that we will resize the domain. Notice that TransAT imports objects as obstructions in the flow domain. We want the object to define where the flow is, so we will invert the fluid-solid domain. Now we can begin and set up our domain and grid. We'll define the following coordinates for our domain. Next, we'll set cells for our domain with 70 in the x direction, 150 in the y direction, and one cell in the z direction. We'll leave the default cell ratio in the x and y direction, but change it to 1 in the z direction. Now we will define a customized refinement. To do so, enable the refinement type, Customize Refinement, and set the properties. We'll create a point in the x direction at a location of 1.55, and we'll create a y point at 4.05. Now we can see our new cell refinement. Continuing, we will divide our domain into 4 blocks and set up our boundary conditions. We will be defining several inflows and outflows. First, let's set the properties of the inflow of our mixture. We'll set a velocity-based constant condition, and we will not set any values for the mixture. Next, we'll go to the Turbulence tab and set a turbulent intensity of 0.1, and we'll set an eddy viscosity ratio of 100. We will now define the properties of our phases and the velocities of our phases in the End-Phase Algebraic Slip Model tab. We will have 3 phases, the first phase being gas, the second phase as oil, and the third phase as water. We will set the following volume fractions entering the domain. And now we will set a velocity for each phase entering in the u direction. For our gas exit, we'll be defining a pressure outlet condition. Our oil exit will remain an inflow, but due to the velocity direction defined, the fluid will actually be exiting. we'll set a constant velocity-based condition, and we do not need to set turbulence as the flow is exiting. Under our n-phase algebraic slip model, we'll set our second phase to a volume fraction of 1, so only oil will exit, and we'll set a velocity in the u direction of 0.423 for each phase. Lastly, we'll define the inflow of the water exiting the domain. We'll set constant velocity-based conditions again, and under n-phase algebraic slip model, the volume fraction of water will be set to 1, and the velocity of each phase will be set to negative 0.105. Now we need to assign boundary conditions to our surfaces. If I reorient the view a bit, we'll see we want our mixture entering on the x0 surface. We want the oil exiting on the xmax 0 surface, water exiting in the y min 0, and gas exiting the top. We will leave the z surfaces empty as they will be set by default to symmetry conditions. With our domain and boundary conditions defined, let's save our project. And we'll be informed that Immerse Surfaces feature will be activated. Continuing, we will set the physical models under the Input tab. For basic equations, we will be solving for pressure, u, and v velocity. We will define gravity in the negative y direction and enable hydrostatic. Under advanced models, we'll be using turbulence modeling with the RANS model and the multiphase flow method with the phase average model. We'll set the properties and we'll increase the number of phases to 3. We'll activate drift velocity and leave the rest of the values as default. We'll ensure that turbulent dispersion is activated. For our phases, our first phase will be gas. And set it as a gas. The second phase will be oil. And our third phase will be water, imported from the material library. Continuing, we will set our simulation parameters. We will have an unsteady simulation with 60 seconds simulation time. The max number of time steps will be 10,000 to ensure that we run the entire simulation time of 60 seconds. Under advanced options, we'll set the initial time step of 0.001 and leave the default number of iterations per time step at 20. We'll also leave the default auto-relaxation factor of 0.6. We'll set adaptive time stepping values with a CFL limit between 0.5 and 1, and diffusion between 1 and 2. For equations, we'll select all quantities and increase the convergence tolerance to 1 e to the negative 2. We will skip initial conditions because this will be defined from a file. For output management, we'll format it to pair view every 100 time steps, and we'll output the variables pressure, u and v velocity, density, viscosity, solid step function, phase volume fraction, phase velocities, turbulent kinetic energy, turbulent dissipation rates, and the eddy viscosity ratio. We'll ensure that non-dimensional numbers are selected. This finishes the setup of our problem. We'll continue to the Execute tab and save our project. Because our multi-phase simulation is slightly more complicated, we cannot set up the initial conditions directly from TransAT. We'll be using the Advanced Initial Conditions feature. To do so, we'll click on the Make Initial Conditions. We can create a file. When there is no initial conditions file, this will load a template initial conditions C++ file. However, this is not what we want. Rather, we would like to load the initial conditions from the tutorials folder. Through the File Explorer, navigate to the tutorials installed with TransAT. In the oil separation tutorial, locate the initial conditions.csx file. Copy this to your current project directory. Replace any initial conditions file that might be there. Now that we have the correct initial conditions file, we can compile the initial conditions. We'll be informed by TransAT that the initial conditions were successfully compiled. We are now ready to run our simulation. We can increase the number of processors and begin. With the simulation in TransAT finished, I've loaded the data into PairView to visualize the results. For this visualization, we'll be creating a clip. Under the clip, we'll change the type to scalar and choose the EMBI scalar with a value of 0. This will create a contour of our surface. If I click Apply, we'll see the object. What we want is the area inside of our separator. Next, I will change the coloring to density. And what we'll notice is we have a very high value of density. This is because it's showing partially the density of the object. Under scaling, we can rescale to a custom data range, and we can change our maximum value to 1000, or that of water. And we'll rescale. Now we can play the animation. And from the simulation, we can see how each phase is removed from each specific exit. This concludes the tutorial of oil separation.